I want to begin with something that will sound strange, perhaps even paradoxical, but I ask you to bear with me. The opposite of a correct statement is a false statement. But the opposite of a profound truth may well be another profound truth. I have spent my entire life thinking about what this means, and I can tell you it is not a philosophical game. It is the structure of reality itself. Consider light. You have seen it, of course. It illuminates your room, casts shadows, reflects in mirrors. Now I ask you a simple question. What is light made of? Your intuition, quite reasonably, suggests it must be one thing or another. Either light is a wave like ripples spreading across water, able to bend around corners and interfere with itself, or light is a stream of particles, tiny bullets of energy that travel in straight lines and bounce off surfaces. This seems perfectly logical. Everything in your experience tells you that something cannot be both. An ocean wave is not a collection of baseballs. A hailstorm is not an undulation in some invisible medium. They are fundamentally different categories of existence. And yet, when we look carefully at nature, when we actually perform the experiments, measure the phenomena, force reality to answer our questions, we find that light is both. Not sometimes one and sometimes the other. Not one disguised as the other. Both, simultaneously, irreducibly, paradoxically. The wave description is correct. The particle description is correct. And here is what troubles people most. You need both descriptions to account for what we observe, but you can never use both descriptions for the same measurement at the same time. This is not a limitation of our estimates. This is not a gap in our knowledge that future science will fill. This is the way nature is constructed at its most fundamental level. Let me be more specific, because I do not want you to think this is merely abstract speculation. Take an electron. You want to know where it is. This tiny constituent of every atom in your body. So you measure its position and you find it here. At this point in space, success. But now ask, how fast is it moving? In which direction? And here is where the strangeness begins. The more precisely you determine where the electron is, the less precisely you can know its momentum, its speed and direction. This is not because your measurement device is clumsy. This is not because you disturb the electron by looking at it, though that happens too. No, this is something deeper. The electron does not have a precise position and a precise momentum simultaneously. Those properties do not exist together in nature. They are complementary descriptions, and nature allows you to have one or the other, but never both at once. You see the problem now. Your entire understanding of reality built from childhood, from watching balls roll and cars move, and least fall assumes that things have positions and velocities at the same time. An apple falling from a tree is somewhere and is moving at some speed, and both facts are true simultaneously. This is so obvious it feels absurd to even state it, and yet at the atomic scale this is simply false. Not approximately false. Not technically complicated. Fundamentally, irreducibly false. I can see the question forming, which is it really? Does the electron really have a position and we just cannot measure its momentum precisely? Or does it really have a momentum and we just cannot pin down its location? And here I must tell you, gently but firmly, that question has no meaning. You ask in nature to conform to your classical intuitions, and nature is under no obligation to do so. The electron does not really have definite values for both properties hidden somewhere, waiting for us to discover them. The properties themselves do not exist in that definite form until we choose which one to measure. And when we make that choice, when we perform that measurement, we create one kind of reality at the expense of another. This is what I have called complementarity, and it is perhaps the most important insights emerged from our study of the quantum world. You cannot have a complete description using only waves. You cannot have a complete description using only particles. You need both, even though they contradict each other in the classical sense, even though they cannot be applied simultaneously to the same phenomenon. Both are true, both are necessary. Neither is complete, and that is not a flaw in our theory. That is the nature of reality itself. Now let me show you what I mean with an experiment. So simple a child could understand the setup, yet so profound that it reveals the foundations of existence. We take a source of light or electrons, the principle is the same, and we shine it at a barrier with two narrow slits cut in it. Behind the barrier, we place a screen that records where the particles arrive. What do we expect to see? If light is made of particles, we should see two bright bands on the screen, one behind each slit, just as if you threw sand at a wall with two openings. Simple, obvious. But that is not what we see. Instead, we see an interference patterning bright and dark bands spread across the screen. This is the signature of waves. When waves pass through two slits, they spread out and overlap. And where the crests of one wave meet the crests of another, they add together and create a brightness. Where the crest meets the trough, they cancel and create darkness. This is what water waves do. This is what sound waves do. And this is what light does, which seems to prove that light is a wave, not a particle. But now consider this. We can turn down the intensity of our light source until we are sending one photon, one particle of light at a time. One individual quantum of energy, indivisible, arriving at the screen and making a single dot like a bullet hitting a target. Surely now we will see the particle behavior. Surely a single particle cannot interfere with itself. Surely it must go through one slit or the other. And yet, even sending one photon at a time, if we wait long enough for many individual impacts to accumulate, we still see the interference pattern. The same alternating bright and dark bands gradually emerge. Each photon arrives as a particle, a single localized impact. But the pattern they collectively form can only be explained if each individual photon somehow went through both slits simultaneously and interfered with itself. You want to object. You want to say, let us simply watch which slits each photon goes through. Let us put detectors at the slits and solve this mystery once and for all. And we can do exactly that. We can measure which path each photon takes. But then here is the crucial point the moment we do. The interference pattern disappears. When we watch which slit the photon goes through, it behaves like a particle going through one slit or the other, and we see two bands on the screen, not the interference pattern. The act of observation, the act of measurement, fundamentally changes what happens, not because we are clumsy, not because our detectors are crude, but because the question, which slit did it go through, is incompatible with the question, what is the interference pattern? There are complementary descriptions, and nature forces us to choose. This is not a trick. This is not an illusion. This is quantum mechanics showing us something profound about the nature of reality. Before we measure which slit the photon goes through, it is not the case that the photon went through the left slit or the right slit, and we simply do not know which. No, before measurement, the photon exists in what we call a superposition R state, that is genuinely both or neither, or something for which our classical language has no adequate words. The wave function, as we call it mathematically, describes this state of potential, this glove of probability that collapses into definite reality only when we measure. I know this sounds mystical. I know it sounds like I'm saying consciousness creates reality, or that the universe is not real until we look at it. But that is not quite right. And here I must be very careful with language, because language itself was built for the classical world and begins to fail us at the quantum boundary. What I am saying is this. The properties we measure, position, momentum, which slit the particle went through, do not exist in a definite state independent of measurement. They are potentialities, not actualities, and the act of measurement actualizes one potentiality at the expense of others. You might think this is just philosophy, abstract speculation about the nature of reality with no practical consequence. But you would be wrong, and I can prove it. The device you are using to watch this, your phone, your computer, would not function if quantum mechanics were not true. Every transistor in every integrated circuit relies on quantum tunneling, a phenomenon where electrons pass through barriers they could not possibly cross, according to classical physics. They do so because their wave function extends beyond the barrier, because they are not localized particles until they are measured. Billions of transistors, billions of quantum events, all functioning exactly as the theory predicts, every second of every day. Fight and see there the atomic clocks that make GPS navigation possible. They measure time by counting oscillations of cesium atoms transitioning between energy levels. energy levels that only exist because electrons in atoms can only occupy certain discrete states, another purely quantum phenomenon. The precision of these clocks is so extreme that they must account for relativistic effects, but the very mechanism of their operation is quantum mechanical. Without quantum theory, without the Copenhagen interpretation that I and my colleagues developed, we could not explain why these clocks work, let alone build them. Or take magnetic resonance imaging, which lets doctors see inside your body without cutting you open. It works by manipulating the quantum spin of hydrogen nuclei in your tissue spin, being yet another property that has no classical analog, a quantum characteristic that is neither rotation in the ordinary sense nor anything else we have words for. The mathematics describes it perfectly. The experiments confirm it, absolutely. But our everyday language cannot capture what spin really is, because there is no classical equivalent. So this is not speculation. This is not metaphysics divorced from reality. This is the foundation of our technological civilization. We have learned to manipulate individual atoms, to control quantum states, to build devices that harness the very strangeness I am describing. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions have been confirmed to better than 1 part in a billion. And yet, and this is what troubles people, we cannot fully explain what it means. Here is what I believe, what I have come to understand through decades of thought and discussion and argument. Quantum mechanics reveals the limits of human knowledge, not because we are ignorant, but because nature itself does not contain the answers to certain questions. There is no deeper reality hiding beneath the wave function, no secret variables that would restore determinism and common sense if only we could access them. The probabilistic nature of quantum mechanics is not a gap in our understanding. It is the fundamental character of reality. This troubles people. Einstein never accepted it. He insisted that God does not play dice, that there must be some deeper deterministic layer we had not yet discovered. And I had to tell him as gently as I could, Albert, stop telling God what to do. The universe is under no obligation to match our philosophical preferences. If nature is probabilistic at its foundation, if certain questions genuinely have no answers until we choose to ask them, then we must accept that, not because we like it, not because it makes sense, but because that is what the experiments show again and again with perfect consistency. But now I want to address something deeper, something that gets to the heart of what quantum mechanics teaches us about knowledge itself. You have been trained by your education and your experience to think of observation as a passive act. You observe the moon, and it is there as whether you look or not. You observe a chair, and your observation does not alter the fact of the chair's existence. This seems self-evident, and for large objects, for the everyday world of experience, it is approximately true, close enough that the approximation never fails. But at the quantum scale, observation is not passive. It is an interaction, an intervention, a collaboration between the observer and the observed. You cannot separate the measuring device from the measured system. You cannot stand outside nature looking in. You are part of the system, and the questions you choose to ask, which property you choose to measure, shape the reality that emerges. Not because you are special, not because consciousness is magical, but because measurement is a physical process, an interaction that creates definite outcomes from quantum potentialities. This is perhaps the hardest thing to accept. We want to believe in an objective reality existing independently of observation, a universe that is out there, regardless of whether anyone is looking. And for practical purposes, for the world of tables and chairs and planets, this is a useful approximation. But it is not fundamental. At the quantum level, the distinction between observer and observed breaks down. The properties we measure are created through the act of measurement. They do not pre-exist in definite form, waiting to be discovered. You might ask, does this mean reality is subjective? Does it mean anything goes? That the universe is whatever we want it to be? No. Emphatically no. The outcomes we get are constrained by the mathematical structure of quantum mechanics. We cannot choose what result we get. That is determined by probability, by the amplitude of the wave function, for each possible outcome. What we can choose is which question to ask, which property to measure, and that choice is real, with real consequences, permanently excluding other complementary measurements. Think of it this way. Imagine you have a coin that is not yet heads or tails, not a coin that is one or the other, but hidden from view a coin that is genuinely both and neither until you look. When you flip such a quantum coin and observe it, it becomes heads or tails at that moment, not before. You did not control which it became. You did not make it heads by wanting heads. But you did actualize one possibility at the expense of the other. Before your observation, the coin existed in superposition in a state of pure potential. After your observation, it is definite. And here is the crucial point. Other observers, making the same measurements, will get the same result. The reality you created by measuring is objective for all subsequent measurements of that same property, but it is not independent of the measurement process itself. This is why I have always insisted that we must be very careful with our language when discussing quantum mechanics. The words we use, particle, wave, position, momentum, reality, observation, all come from the classical world. They work perfectly well for describing billiard balls and ocean waves. But when we try to apply them to electrons and photons, they begin to fail. Not because we are using them wrong, but because the phenomena they attempt to describe do not fit into classical categories. So we are forced to use complementary descriptions, seemingly contradictory concepts, both necessary and both incomplete. We speak of wave-particle duality, not because quantum objects are sometimes waves and sometimes particles, but because we need both concepts to give a full account of quantum behavior, even though we can only apply one at a time to any given measurement. We speak of the uncertainty principle not as a limitation of measurement technology, but as a fundamental feature of nature that conjugate properties like position and momentum cannot both be definite simultaneously. And here is where it gets truly strange, where even I must admit that our understanding reaches its limit. The wave function. This mathematical object that describes the quantum state evolves deterministically, predictably, according to Schrödinger's equation. Given the wave function now, we can calculate the wave function at any future time with perfect precision. And yet, when we measure, when we observe, the wave function collapses instantly and unpredictably to one definite outcome. The evolution is deterministic, the collapse is probabilistic. Both are parts of quantum mechanics. Both are necessary to describe what we observe, and we do not fully understand how they fit together. This troubles me less than it troubles some people. I have never believed that physics must provide a complete, intuitively satisfying picture of reality. Physics describes what we can measure, what we can predict, what we can control. It provides a framework for calculation, for understanding regularities in nature, for building technology. But whether it reveals some ultimate truths about what is really going on, that is a different question, perhaps not even a meaningful one. What we can say is this: quantum mechanics works. It works better than any theory we have ever devised. It describes atoms, molecules, solids, semiconductors, lasers, nuclear reactions, the behavior of matter at every scale we can access. The predictions are testable. The tests are passed. The applications are everywhere. And the interpretation I have defended, the Copenhagen interpretation, as it came to be called, provides a consistent framework for understanding these predictions, even if that framework includes irreducible complementarity, fundamental uncertainty, and the active role of measurement in creating definite reality. You might wish for something more. You might want a theory that preserves determinism, that gives you classical intuitions back, that allows you to say what the electron is doing when no one is watching, and perhaps someday someone will find such a theory. But I will tell you what I think. I think we have reached the limit. I think quantum mechanics is showing us something profound and final about the nature of knowledge itself, that there are questions nature simply does not answer, not because you lack information, but because the questions themselves presuppose a classical reality that does not exist at the quantum level. This is not defeat, this is not ignorance. This is understanding that reality is richer and stranger than we imagined, that our classical concepts are approximations valid only in a limited domain, that at the foundation of existence we encounter genuine mystery. Not mystery in the sense of something we might someday solve, but mystery in the sense of something that exceeds the categories of our thoughts. Let me return to where we began. The opposite of a profound truth may well be another profound truth. Light is a wave. Light is a particle. Both statements are true. Both are necessary. Neither is complete. You cannot have a full description using only one. This is not contradiction. This is complementarity. And once you see it in quantum mechanics, you begin to see it everywhere. Causality and freedom. Determinism and choice. The predictability of the wave function and the randomness of measurement outcomes. These are not flaws to be eliminated. They are the structure of reality itself revealing itself to us in the only language available. The language of mathematics supplemented by classical concepts pushed to their breaking point. We have learned to calculate with extraordinary precision. We can predict the energy levels of hydrogen atoms to 10 decimal places. We can design quantum computers that exploit superposition for computation. We can build devices that manipulate individual electrons. But we have also learned humility. We have learned that there are limits to what can be known, not because of our limitations as observers, but because knowledge itself has boundaries. I do not know if this is satisfying. I do not know if it gives you the closure you might want. But I can tell you that it is true as far as truth can be established by experiment and observation. The quantum world does not behave like the classical world. It cannot be forced into classical categories. It requires new ways of thinking, new modes of description, a willingness to accept that nature is under no obligation to conform to our intuitions. And perhaps, and this is my deepest conviction, perhaps this is exactly as it should be. We are not observers standing outside nature, looking in at an objective reality that exists independently of us. We are participants. We are part of the universe trying to understand itself. And the act of understanding, the act of measurement, the act of asking questions and receiving answers is itself part of the physics. We cannot be separated from what we study. Subject and object, observer and observe, are complementary aspects of a single, unified reality. This is what quantum mechanics has taught me. Not just the mathematics, though the mathematics is beautiful and profound. Not just the technology, though the applications have transformed our world. But something deeper, a lesson about the limits and possibilities of human knowledge, about the irreducible role of complementarity in our descriptions of nature, about the fundamental mystery that remains even when we have calculated everything we can calculate. Physics has given us the power to split atoms, to manipulate quantum states, to peer into the structure of matter with incredible precision. But it has also shown us the boundary of what can be understood, the questions that have no answers, the paradoxes that cannot be resolved by thinking harder or measuring better. And perhaps that is the deepest lesson of all, that understanding is not the elimination of mystery, but the recognition of where mystery is fundamental, where it cannot be dissolved, but only acknowledged. I have spent my life at this boundary, trying to find language for what happens where language fails, trying to make sense of a world that defies sense-making in the classical way. And what I have found is not certainty, but a framework, a way of thinking that embraces complementarity, accepts uncertainty, and recognizes that observation is not passive discovery, but active participation in the creation of reality. This is the Copenhagen interpretation. This is quantum mechanics as I understand it. And this is, I believe, as close as we can come to understanding the nature of existence at its most fundamental level. Whether this is the final word, I cannot say. Science never offers final words. Perhaps future generations will find something deeper, a theory that makes quantum mechanics as intuitive as Newtonian mechanics once seemed. But I suspect not. I suspect we have reached something fundamental, something that cannot be reduced further. And if that is true, if complementarity, uncertainty, and the role of observation are permanent features of our understanding, then we must learn to live with a universe that is richer, stranger, and more mysterious than we ever imagined.